Okay, take two. Are we live this time? Did I fix it? Did I fix it? All right, I think I fixed it. What's up? How's it going, YouTube? I think that there's one person waiting already, and I already messaged the Discord with this link. I created another one. Super hard to switch YouTube accounts. I was just streaming classical guitar first for a while, and now we're going to practice some mathematics. How's it going, everybody? Let me know if anybody crossed over from the other channel. Today we're going to practice math. We're going to practice linear algebra. It's January 27th, and my handle is JC Practices Math. Last time we did a lap through Frale problems. I was doing the third problem from a bunch of sections, but we didn't get to finishing 1.7 or 1.8. So those are going to be the next problems that we do. For anybody who's new, hello, my name is John. I am a ex-Google engineer. I'm in between jobs right now, so I'm just practicing my passions and hobbies on the internet. I'm a classical guitarist and a former mathematician, and now I want to rebuild my passion and love for mathematics. So the way that I'm relearning linear algebra right now is by going to the first section, solving the first problem, going to the second section, solving the second problem, going to the third section, solving the first problem. So I solve the first problem from every section until I get stuck, and then we reset. I start over from the beginning, I solve the second problem from every section until we get stumped, and then we restart at the beginning again and do the third problem. So we did the third problem from a bunch. Last time I didn't get stuck, but I ran out of time. So we're going to continue from Frale. We're learning linear algebra right now. Oops. And look at all this fancy technology. I wish I had this kind of technology when I was in school. So we're going to work Frale 1.7.3. This is a section where Frale starts introducing Markov chains by way of application to population distribution. So if there's a certain probability that people move into a town and a certain probability that people move out of the same town, like if there's like New York and San Francisco, and the chances that people are moving out of San Francisco and into New York is higher than people moving from New York to San Francisco, then what is the steady state, kind of like final state? There's like a certain probability people stay, there's a certain probability people move, and you create these things called Markov chains. Where'd my book go? Here it is. Okay. So I see we got 3 people watching. Hello. How's it going? I hope you're having a good day. We're going to be working from Frale. This is a beautiful book. It's my favorite book that I've seen out of a bunch of linear algebra books, especially for an introduction to linear algebra. I think it's really a great intro book. It's pretty rigorous. It's not like proof heavy, but there are proofs. You can learn the proofs, and there are clear statements of theorems in this book, even though there's annoying little historical blurbs in the side and things like that. There's some marginalia, but not too much. It's a nice book. It's very clear, very organized, written kind of for undergraduate mathematicians, I'd say, kind of. All right, so Frale 173. Let's freaking go. We have the matrix A as 0.2, 0.1, 0.3, 0.4, 0.5, negative 0.1, 0.4, 0.4, 0.8. And the question is A transition matrix? If so, is it regular? Nope, this one is not, because no, negative 0.1 in a 2, 3. So to be a transition matrix, every entry needs to be non-negative. You can have zeros, but you can't have negative numbers. So there we go. We're done with that one. Let's go. Let me know, everybody. Hit the like and subscribe if you're enjoying this. If you're watching the VOD, say hi. I see that some of the VODs are doing well after the stream, which is nice. That's very promising to me, because I hope that this can be kind of somewhat evergreen content. So nice to meet you all. Please say hello. Let me know what you'd like to see in a math practice stream. The number one thing I'd like to see or hear is some background music. I was going to play this other video, but... Oh, do we already have... Am I live? Is my mic hot? Oh, and we already have background music. Let's go. I didn't realize. Okay, well, that's good. So we got my fall classical guitar recital playing at the same time. All right, 1.8.3. This was a new concept to me. I knew the idea. I knew that this exists, but I had never worked any problems about this stuff before. So this is about Huffman codes, which are error... Wait, why am I saying Huffman? It's Hamming. Hamming. Oh, wait. Is it Hamming or Huffman? Who the hell is Huffman? Huffman is another person. Yeah, I made that up. Hamming. I've been saying Huffman for like 3 days now. Look at that. Hamming. Let's fix it. Hamming. Error correcting codes. It's a practice stream. I'm going to be making lots of mistakes here, because I'm a human. I'm not ChatGPT. All right, so it says, in exercises 3 to 11, consider the 6-3 linear code C with standard generator matrix G equals 1 0 0 1 1 0 0 1 0 1 0 1 0 0 1 0 1 1. What's up, SB Practices? Thanks for crossing over, SB. Good to see you, Siddharth. How's it going, bro? Okay, and the question for question 3 is, give the parity check equations for this code. I have no idea what that means. If I'm going to be completely honest with you all, I have not read this section. So the goal right now is I am taking a problem-solving first approach through relearning linear algebra. I'm going straight to the problems. I'm going straight to the exercises. And if I don't know how to solve an exercise, I read just enough of the chapter to be able to solve that exercise. And then I move on to the next section. That's just my personal preference right now for how to practice math. It's kind of fun because I'm reviewing these topics and seeing a lot of concepts, like even though I'm not solving tons of problems from one concept, it's good to be seeing a lot of different subjects and topics. And my class never taught from this optional section, so I don't know what this is. I don't know what the hell this is. Parity check equations for this code. I'm going to have to actually read this section for this. I don't know where to begin, actually, with this one. And that's okay. Let me read a little bit. Yes, you can imagine that if we encoded all of the 256 ASCII characters in an n by 8 linear code and used nearest neighbor decoding, it would be a job to pore over the list of 256 encoded characters to determine the nearest neighbor to a received code word. That's exactly what I thought. If anybody watches day 2, I believe, or day 3, I think day 2, when I solved this problem, the first problem from the Hamming code, no, it was day 1, I believe. Whatever it was, I think it was day 1. And I solved the first problem, 1.8.1. It took so long. It was such a chore. It was so boring and not worth the time to just manually go through this long list of the Hamming 7.4 code. So now we're going to learn a smarter way to do this of what we did before. Okay, so you can imagine that if we encoded all of the 256 ASCII characters in an n by 8 linear code and used nearest neighbor decoding, it would be a job to pore over the list of 256 encoded characters to determine the nearest neighbor to a received code word. There is an easier way, which we illustrate using the Hamming 7.4 code developed before illustration 4. Recall that the parity check equations for that code... I need to read a little bit of this part, huh? Okay, I gotta read a little bit more, but first off, so we have to read the section, and I'm gonna mark the section in blue. Recall that the parity check equations are, for that code, it says are x5 equals x1 plus x2 plus x3. I know vaguely what a parity check is. We're testing to see if there was a error in transmission of a message. I think that there's somebody at the door, so I have to be right back. Unfortunately, be right back. Okay, I'm back. Alright, we have no problem today. We'll be doing mathematics until 12:55, so I have 35 minutes. Okay, so parity check equations can help you detect if there was an error, like a typo. We use parity check equations all the time in credit card fields. Like, if you have a typo when you're typing your credit card into a form, there are really cool codes, really cool ways to detect typos, even though you didn't transmit the number. Like, your phone is not doing any kind of like lookup of like whether that number is a valid number from a database, but it uses parity check equations like these that can detect, like, well, if here's an incorrect parity check equation. This isn't real, but maybe there's a rule that a credit card number has to have the same number of even numbers as odd numbers. For all I know, that might be true, but I don't think so. Like, if there's more even numbers than odd numbers, then you would know that there's a typo, right? That's a way that there's no intelligence determining whether a credit card number is valid or not. It's like a safety check. It's a parity check. X5 is this, X6 is this, and X7 is X2 plus X3 plus... okay, so these are... Okay, cool. I skipped this part of the section last time. So, Hamming 7-4, let's see if this works. I'm going to take a random number. Hamming codes are about taking a 4-bit number. What's up, Marca Doe, $12.99. How's it going? Welcome to my practice stream. How's it going? So we're going from a 4-bit message, and we're going to translate this using the Hamming 7-4 codes. So I believe that we start with the same original digits. Is that correct? And then we add extra bits. If I understand this correctly right now, so I'm trying to do as little reading of the book as possible to try to understand just from a hint. Can I kind of imagine what the section is teaching? So I was wondering, how did we figure out what these extra bits are? Like, I don't know, it might be 1100 or something. Let's figure out what they are. So X5 is X1 plus X2 plus X3. Yeah. So X1 plus X2 plus X3 is 1 plus 0 plus 1 plus... Yeah, 1 plus 0 plus 1, right? X6 is defined as X1, X3, X4. X1, X3, X4. We'll find out what that is. And then X7, according to this little rule, is X2, X3, X4. X2, X3, X4. Okay? This, I believe, if I understand correctly, X1, X2, X3, X4. So X1 is 1, X2 is 0, X3 is 1, X4 is 0. So let's write those in everywhere here. X3 is 1, and X4 is 0. X2 is 0, X3 is 1, and X4 is 0. This would have saved me time the other day when I solved that other problem. But I learned a lesson in the process. In binary addition, 1 plus 1 is 0, and 0 plus 0 is 0. You always want 0 plus x to equal x. That's like a very good property about 0. Even if you're creating addition in some other kind of numbers, like binary numbers. 1 plus 1 plus 0 is 0. 0 plus 1 plus 0 is 1. So I think that this maps to 0, 0, 1. Is this true? Question mark. If I look up the table, 1, 0, 1, 0. Yep. Bingo. Got it. That's true. So that is in the table. Cool. Now I have a better understanding of how all of these encoded words are built. If I scroll back to the other day and I look at problem 1.8.1, they told us the secret message, a good dog. A good dog. And we had to convert that to Hamming. Well, it's not a secret message, but it's a message, and you want to make sure that it's not corrupted. You want to make sure that your friend gets the message, a good dog. So we converted every letter in a good dog to a binary number, and then we wrote down the Hamming codes for every one of these numbers. Actually, this one was easy. This one was super easy. The problem that I was thinking of that took forever, it was very tedious, was going in the other direction. In 1.8.2, wherever the heck that is, whenever we did 1.8.2, it was super tedious. We got the received message. Here it is. Application to linear binary codes. We got this received message, 0, 1, 1, blah, 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 all of these. The yellow ones were uncorrupted, or I could say expected, maybe is a little bit cleaner. This is an expected message. The red ones were unexpected. Like, you shouldn't receive this number 1010100. That one is not, that is not expected. That's not one of the expected numbers. So we think that it was corrupted. And we had to find the closest expected message, the closest expected number. And yeah, we found that if I do this in green, this number is unexpected. This one is expected. They're very similar, except for this one. The second bit is the only number, the only digit that's different in these two numbers. So it was a typo. Somebody accidentally typed 1 when they meant to type 0. So this math is all about kind of detecting typos. And you can think of detecting typos when you enter your credit card number into the Lyft payment system, which I helped build, by the way. Shout out. Did I mention that I used to work at Lyft? All right, so here we go. Now this is parity check equations for Hamming 7.4. Here's this generator matrix for a Hamming code on 6.3. Because this one is for Hamming 7.4, which means like from a 4-bit message, we add parity bits and construct a 7-bit number. Okay, so let's figure out, how do we figure out the parity check equations given a generator matrix? So I need to read the section a little bit and find where they talk about these generator matrices. And now we're starting to get to some linear algebra. Some actual linear algebra. Okay. So, The equations use 16-bit words, a subset of B7 called the Hamming 7-4 code. It's a binary group code. Cool. We can encode each of the 16 binary words of length 4. Neat. Okay, so the example in the book is for Hamming 7-4. The way that we can get the parity check equations from the generator matrix is by multiplying the vector x1, x2, x3, x4 with the standard generator matrix. 1, 0, 0, 0. Oh, this makes sense. Okay. So here we have the identity matrix. Oh, neat. Okay, cool. I see where the linear algebra is happening now. Heck yeah, that's so cool. Okay, I get it now. 1, 1, 1, 0, 1, 0, 1, 1, and 0, 1, 1, 1. Got it. Okay. So we see that this is the identity matrix joined with, I don't know, I'm going to call this the Hamming or like parity, the parity check equations, right? We have the identity matrix on the left, and then we have these parity check equations on the right. So then, if we go back to our actual problem, I did a little bit of reading of the section. Let's be more intelligent about this. If I go here, can I add a new page? How can I do this more easily? Add page. Okay, great. There we go. Neat. Okay, so now I can see pretty clearly that G is a 3x3 identity matrix with some parity check equations over here. Vector algebra, 3D geometry and stuff. This is vector algebra very much right now. So now I can see that this is, these are the equations. X4 is x1 plus x2. X5 is equal to x1 plus x3. And x6 is x2 plus x3. We could get that very explicitly by multiplying (1, 0, 0, 0, 1, 0, 0, 0, 1, 1, 1, 0, 1, 0, 1, and 0, 1, 1. Scooch that thing over. 0, 1, 1. Right? You can do the matrix algebra here. Just for funsies, I'll show it. X1, wait. Oops. the original code word is like that. This is kind of funny. Am I doing this right? X1, X2, X3. X1 plus X2. X1 plus X3. And... oh, yeah, okay. Oh, derp. Yeah. There's only one row in the left. Here we go. X2, X3. X2. Yeah, so if you do that matrix multiplication, we get a 1 by 7 or 1 by 6. 1 by 6 vector. Or a 6-length vector or a 1 by 6 matrix. Tomato, tomato. But yeah, these are the parity check equations. Cool. All right, well, I had to read a little bit of the section, so I'm going to star that. And let's see how far we can get if we reset. Let's reset. Let's start from the beginning. F and B 114. I forgot after doing it really quick. Yeah, I mean, I'm not very good at visualizing 3D geometry, but there was a problem in 113 just last time in this section. It asked us to sketch these vectors in 3D in 3-dimensional space. I'm not very good at like imagining 3D coordinate. Like, it takes me a while to kind of like to see it and imagine, you know, and see like 3-dimensional space. But yeah, these were the vectors. Red was 1, 3, 2. Cyan was 1, 2, 4. Yeah. So this is like 3-dimensional geometry. Good question, Siddhar. Thank you for asking. Okay, 114. This should be easy. We'll see. 114. We have phi is 2I minus j plus 3k. Funny enough, you're going to see me struggling with some 3-dimensional geometry right now as we speak. Now, the question now is, what is v plus w? And what is v minus w? Let's give this thing another color. Let's also give v a color. So I'm going to compute here, and I'll keep it in the same notation, 5i plus 4j plus 7k. Right? And that's if you added v and w. If you did v minus w, we have negative I, adding here we have 4j again. Oh wait, no, what? No. Negative 6j. And negative k. Cool. And now, it's 2, negative 1, 3. What's the greatest components? We have 7 in the k axis, and we have -6 in the j axis. So I don't think we don't need a whole lot of k, negative k, that is. So like 1 unit down in k. 1, 2, 3, 4, 5, 6. Positive. Oh, 7. We need 7. Yoink. We need in the j axis, we need -6. 1, 2, 3, 4, 5, 6. Right? And we need +5. 1, 2, 3, 4, 5. And then in the I component, for whatever reason, I moves closer to you. We need 5. 1, 2, 3, 4, 5. 5 positive and at least -1 negative. So that gives some sense of like how deep that might help, like a little bit. It helps me right now kind of get a sense of this 3-dimensional coordinate grid. V is 2i, again, this axis that's pointing in and out of the page. 2i minus j. So we're going to go 1 unit minus j and +3k. 1, 2, 3. Something like that. So, boop, boop, boop. Yeah, something like that. I don't know if that makes sense. I don't know if it helps to draw more, but yeah. W 2, -1, 3. 2, -1, 3. W is 3, 5, 4. 3, 5, 4. So 1, 2, 3, 5 positive. 1, 2, 3, 4, 5. Five positive J and 4 K. 1, 2, 3, 4. If I was clever, I could like try to change the width to be getting closer or farther of these vectors, but I'm not that clever. But you could do that. Red. V plus W is 5, 4, 7. Green, we'll go ahead and write this. -1, -6, -1, -6, -1. One, two, three, four, 5. 1, 2, 3, 4. And 1, 2, 3, 4, 5, 6, 7. So these grid lines just help a little bit seeing like parallel lines where everything is I think that's right. 5, 4, 7. And then -1, -6, -1. -1, -1, 2, 3, 4, 5, 6. And then -1, -6, -1. So it's here. Kind of hard to visualize. It's hard for me to visualize. Garagon, what's up, man? Thanks for joining the math stream, even though you find it disgusting, nauseous. There's some cool stuff here, bro. There's cool stuff. I'm telling you. All right, let's go. Frale and Beauregard, 1.2.4. I'm here to heckle. Please do. I need the engagement, dude. Please. Encouraged, not just welcomed. Encouraged, dude. All right. U is -1, 3, 4. That sounds familiar. Didn't we just use that one? V is 2, 1, -1. 2, 1, -1. And now this question is asking us to find U plus V. Really? Wait, no. We're looking for V minus 2U this time. V minus 2U. Well, V minus 2U would be the magnitude of the vector 4 we've got 1 minus 6. And we've got -1 minus 8. The magnitude of that vector is the square root of the sum of squares. Whatever, who cares what that is? 30, 41, 130, Luna's distracted me. Alright, we've got 41 plus 81 would be, 132. Wait, 41 plus 81, I'm bad at math. 41 plus 81 is 122. Which is 2 times 61, right? And 61 is prime. Is that right? 61 is prime. So I think we're done. If it weren't for Tango and Sky, I'd be bleeding from every orifice from sheer disgust. Bro, you should be marveling in the beauty of mathematics. Luna. Okay, we've got more dopamine for you, Garagon, right over here. Kitty cat, hey, don't scratch. Okay. Alright, y'all, people watching the VOD, I see you. I see you in the analytics page. Leave a comment if you're enjoying this. If you're still watching, leave a comment. Say hi to my cat. Her name is Luna, and she's so cute. Everybody loves the Luna. Everybody loves this cat in my other stream. I have another channel, JC Practices. I practice classical guitar. That's what we're listening to right now in the background. And she deserves her own channel, doesn't she? Should Luna get a channel? I think she should. Math is the devil's scratches. Yes. What a cute cat. Isn't she? Isn't she a cute cat? What's up, Marcado? Yeah, she's adorable. She will be jumping up in the camera, like, she'll be up in the camera and all sorts of hilarious stuff at times. What time is it? I gotta go soon. I gotta go, like, right now. Thanks everybody for hanging out with me today. My name is JC Practices Math. At JC Practices is my guitar channel. I also obviously have this channel. And I also have a gaming channel. So, if y'all want to subscribe and help me grow as a YouTuber so I can try to make it as an independent artist, go follow my other channels. Thank you for watching. Please leave a comment and like and subscribe if you enjoyed this. And if you didn't enjoy this, feedback is an absolute gift. You know, if you want to leave a comment, if you're still watching and you hear this and you don't want to subscribe, I would love to know why. How can I? JC Practices Meth. Yeah, if I get desperate, we'll turn into Breaking Bad, and that'll be the next channel for sure. For sure. Good to see you, Garagon. Nice to meet you, Marcado. And take care, everyone. If you're watching the video, nice to meet you. Leave a comment in the comment section, and take care. Bye. Bye, everyone. Bye.